Okay, boys and girls, students of pre-calculus, what I'm going to be doing is 5.6, which we're going to be talking about rational functions and how you graph rational functions and everything. Should have done this in college algebra. Okay, first thing we want to look at is what is a rational function? Okay, so rational function just basically means you have a ratio of two polynomials. And the denominator can't be zero because you can't divide by zero. Okay, and I say, let's see, the denominator has to have a polynomial of at least degree 1, which means it has to at least have a variable x in it. The numerator can just be a constant, but the denominator absolutely has to have a whole number power of x. Okay, so here's a couple of examples. P of x, okay, all we do is we make a fraction. The denominator, you could have x squared minus 1. That's a polynomial. The numerator, you could have another polynomial. That is a rational function. Okay, here's another one. Okay, this time I'm just going to say x plus 2. That's a polynomial. It's got an x in it. And the numerator could just have a number in it. So I can go like that. So you're just looking at ratios of polynomials. Okay, so we have certainly talked about the domain. We've talked about domain already, so what we're going to be doing on this is a rational function. So when you're doing a domain of a rational function, it'll be the set of all real numbers excluding any value that causes the denominator to be zero. Okay, so what we do is we're always just trying to set the denominator equal to zero and solve the equation. And then that'll tell us what we have to eliminate from the domain. Okay, so on this example 2a here, well, we can do this in your head too. It's just set the denominator equal to zero, solve the equation. So if x is equal to negative 5, see, it makes a zero denominator. So if you have 10 times negative 5 over negative 5 plus 5, that's undefined, but that's the only value of x that makes it undefined. So set builder, we could just say set of x, such that x is a real number. You can actually leave that x as a real off and just put x cannot be equal to negative 5. So that's the proper way to write set builder notation, is like that. Two braces, set of x, such that that vertical bar is saying such that. So if you're doing interval notation, there's just going to be everything below negative 5 and everything above negative 5. So that's our way of excluding, and you want to make sure that you use parentheses around that negative 5, because if you put a bracket, then you're telling me negative 5 is okay to include in the domain. Okay, so that goes like that. Okay, next problem, we do the same thing, just look at the denominator. So we're just going to set x squared minus 9 equals 0. There's two ways you could solve this. One way to solve this is to isolate the x, square root both sides. And when you actually do the act of taking a square root of both sides, you have to introduce two answers. There's a plus and there's a minus. So what you would have on your set builder notation is you'd say set of x. And again, you could put x as a real number, or you could leave that off and just say x is not equal to negative 3 and 3. It's also okay to say x is not equal to plus minus 3 as an abbreviation. Okay, so that would be your domain. Okay, if you're doing this in an interval, now what you kind of have is you have negative 3, you have 3, and then you have everything in between. So you have three intervals. So you have to be everything below negative 3, everything between negative 3 and 3, and everything bigger than 3, like that. So that's how you would write that in a interval notation. Okay, wanted to mention you could also do this problem this way. You could factor x squared plus 9 is a difference of two squares. So you could do it that way and then just solve these two equations. You know, you should have done this a lot in a college algebra class, so it goes like that. Now, one thing I want to mention, and I want to use a graphing calculator on this video some. So this is actually a free, if you go to ti84calc.com, there's some nice free TI-84 calculators on here that you can use. So if I was going to graph this, I would have to put the x minus 1 in a set of parentheses, and then I would have to put the x squared minus 9 in parentheses, because if you don't do that, it's not going to follow the order of operations. So I just wanted to show you what I like to do when I graph is, instead of setting up a window, if I press my window button, it's automatically set up in what we call a standard window. It's going negative 10 to 10 on the x-axis and negative 10 to 10 on the y-axis. When I graph, I usually tell students to just go zoom number 6, and that automatically puts it in a standard window. Okay, so they're going to find, when you look at your table of values right here, if you go second graph to open up the table of values, you're going to find that there's an error at 3 because the calculator is dividing by 0, and there's an error at negative 3. So if you put something in a graphing calculator, it's going to tell you where things are undefined on a rational function, but you want to be able to do this without having to rely on your graphing calculator. Okay, next thing we'll look at this. Now, something that's kind of important on this one, what we're going to do is the numerator does not factor. You just leave that alone, but the denominator does factor. Students a lot of times need refresher on factoring. If your factoring is not good, then you absolutely have to get it under control. This semester, you get into calculus, you can't factor, you're going to be in a world of trouble. So, teachers teach this different ways. This type of a trinomial is just creating a FOIL problem in reverse. The first term can only be x times x. Students don't usually have any issue with that. The last term is 15, so you are looking for numbers that multiply to give 15. And there's only two possibilities, 1 and 15 and 3 and 5. But what you're doing is you're looking at that inner term will tell you which one's right. You got to make these things add up to negative 2. So there's no way to make 1 and 15 add up to negative 2, but there is a way to make 3 and 5 add up to negative 2. So that just means you're going to have a 3 and a 5 with a plus and a minus. Anytime you factor anything, check your answer by foiling it and see if you're right. And students are horrible about that. When you do something in math, check it. Do something and check it. Do something and check it. If you want to become a good math student, I'm not kidding, that's what you got to do. So here's what happens. Now you're going to say, okay, that cancels. Yes, it does cancel, but it does not eliminate this from the domain. So what you have to do is you have to still solve these two equations. Don't cancel it out and ignore it because you're going to miss part of your domain. So this is x equals negative 3. This is x equals 5. See, what happens in the original problem, both negative 3 and 5 cause you to have a 0 denominator. So we'll write this as set of x. Again, we could put the real number, but you can leave that off, and we just say x is not equal to negative 3 and 5. Okay, interval notation is 3 intervals. Everything to the left of negative 3, everything in the middle of negative 3 and 5, and everything bigger than 5. So this would be the two ways that you write your domain. Again, if you graphed this on the calculator, you would find, if you put this in your calculator, the original, you would find errors at negative 3 and 5. But if you put in the version after the cancellation, it would only give you an error at 5. So you have to kind of be careful about that. Okay, so the first thing I'll have you do is do a couple of problems down here at the bottom where you're finding domain. This is a good time to see how good you are at your factoring. So pause the video, resume when you are ready to check. Okay, so you want to go ahead and look at your work, and it's important when I give you these videos, I never know if students pause the video and do work or they just copy it down. If you want to learn, then you want to do it the way I asked you to do. You want to pause, work problems, and see, sort of self-check yourself. Okay, think about that. I mean, you want to do whatever makes you learn the best. And this is better than just blindly copying stuff down. All right, so first one, you're going to find you just set the denominator equal to 0. That results in negative 5/3. So you can see how I wrote the set builder and interval notation. Second one was the same thing. I factored that denominator. Okay, you had to have factored that correctly, and that would give you negative 8 and negative 2. So it's all real numbers except negative 8 and negative 2. And then the last one, now sometimes these last two are the ones that students have issues with factoring. So when you look at this denominator, you can take a common factor of 2 out. Once you do that, you have 2x squared minus 1. And when you've got x squared minus 1, this is what we call a difference of two squares. So if you have a difference, a subtraction symbol, and these are squares because 1 times 1 is 1, and because x times x is x squared. So the factoring on this is the easiest there is. You just go x and x, 1 and 1, with a plus and minus. The reason it's always plus and minus on a difference of two squares is because when you FOIL this, you want the inner term to cancel. See, this is not a trinomial. This is what we call a binomial, and that middle term is not there, so it's got to cancel out. Okay, so you got that. So anyway, set these two factors to 0. Don't worry about the 2. That doesn't have any bearing. You don't set 2 equal to 0. That's nonsense. Okay, next problem. I'm going to review how to factor this one also, because this is the one that students do a lot of different ways. And I'm telling you, over 50% of students in my Calculus 1 class cannot factor this kind of trinomial. And you've got to get this under control. Now, I'm going to show you how to do trial and error. Any mathematician is going to do this by trial and error. You don't have to do factor by grouping or whatever you've been taught. You know, do what you're comfortable with, obviously. But, you know, your first term, the only possibility is 2x times x. Your last term, the only possibility is 5 times 1. Now, the middle term works a little bit differently. Whenever you have a number in front of x squared, it's a little different. So what you do is you just draw 2 parentheses, and you have to write this down. You got to understand, you can't do this problem in your head. You have to see something on your paper. So if I was to go through and put just 5 times 1, 9x out of this. So that would be 5x. The outer term would be 2x. There is no way to make that add up to negative 9x. So that means that failed. Try it though. Now, if 5 and 1 don't work, it might work if you do it backwards. That does make a difference. So put a 1 and 5. Now do the same thing. 1 times x is 1x. 2x times 5 is 10x. Now ask yourself the question, how do I make 1 and 10 add up to negative 9? Well, if 1 is positive and 10 is negative, then you got it made. So plus goes there with the 1, minus goes with the 5. Okay? Work on that, okay? I would love to teach a Calc 1 class before I retire where every student can factor without any problem. You can overcome this if you work on it. Okay, all right, so that will kind of get you through those problems, and we'll go ahead and move on. Okay, next thing we're going to look at is what we call a vertical asymptote, and I do want to go over this clear enough that you understand why we have a vertical asymptote and what they really mean. So a vertical asymptote occurs on a rational function where the reduced form, and that's real important, is undefined. So to find a vertical asymptote, you got to reduce the rational function. What I mean by that is if factors cancel, then cancel something out, then set the resulting denominator equal to 0. You're finding where it's undefined, but you're only finding where the reduced form is undefined. Okay? So the idea is as x gets close to a vertical asymptote, the y value will either go to infinity or negative infinity. So here's a couple of illustrations of the way this goes. So vertical asymptote, like on this, the vertical asymptote is x equals negative 3. A vertical line is always named by the x value it goes through. X equals negative 3 means it's a line where x is always negative 3 and never changes. If x is negative 3 and doesn't change it, that's what forces it to be a vertical line. So this is some notation you may or may not be familiar with. If I do this, this is saying x arrow negative 3 negative. Well, the arrow means approaches. So if you kind of look what I have up here, this says x is approaching 4 from the left. The reason it's approaching from the left is that superscript is a negative. The next one says x is approaching 4 from the right. If the superscript is positive, it means it's from the right-hand side. So what this means, if you're coming from the left, if you look at this graph's going up. The graph's going up, so that means f of x is going to positive infinity. Okay, if we're coming from the right, which is here, the graph's going down. If the graph's going down when you get close to the asymptote, then it's going to negative infinity. Okay, so this is something that you'll do in a Calculus 1 class. It's good to get the idea. You'll learn what's called a limit in Calc 1. Okay, next problem, we have a vertical asymptote at x equals negative 3. And we have another vertical asymptote at x equals 3. We usually represent those with a dashed line. Okay, so now what we're going to look at is, see, we're approaching negative 3. But on this, we're approaching from the left. So if we're approaching from the left, that graph is going up. So that means that's going to positive infinity. Okay, the next one, we're approaching negative 3 from the right because of that superscript. If we come from the right, the graph is going down as it gets close to the asymptote. So that would be approaching negative infinity. Okay, now we're looking at 3. We're approaching 3. But if we approach 3 from the left, the graph is going up. So that's positive infinity. You're never going to hit the asymptote. You're just going to get close to it. And then if you're coming from the right, because of the superscript, the graph is also going up. So that's positive infinity. So this is just a way to represent, is the graph going up infinitely or is it going down infinitely? So that's something that you want to be familiar with. Okay. Moving to the next thing, we're just going to focus on finding the equation of a vertical asymptote. So this is very similar to the domain. You look at the denominator, and in your head you can tell that if x is 1, then you've got a 0 denominator. So just solve the equation. You get x equals 1. So that would be your vertical asymptote. Okay, do the next one. We need to factor the denominator. The numerator does not factor. It's important, too, that you pay attention to both the numerator and denominator, because sometimes something will cancel. So with this one, if we factor this, first term is going to be x and x. Then you've got 12. So you got 1 times 12, 2 times 6, or 3 times 4. Since the middle term is 4, you're going to do a 2 and 6. Okay, I usually teach students to do the signs at the last. You don't have to do this, but 2x and 6x are supposed to add up to plus 4x. The way to make that happen is the 6 has to be positive and the 2 has to be negative. If you take the time to write this stuff out that I'm shading in blue, That'll help you. You won't go wrong if you do that. Okay, so anyway, what we have, there's no cancellation. So what we do is we do x minus 2 equals 0, and then we have x plus 6 equals 0. Solve the equation, we get x equals 2, and then we have x is equal to negative 6. So this particular problem has two vertical asymptotes. Now, what I want to show you on this is why a number goes to infinity or negative infinity. Okay, it's important to understand that, not just blindly memorize that, hey, the teacher told me so, so it's got to be true. So if you have 1 over x minus 1, if we were looking at a number very, very close to 1, like, say, x is equal to 0.99, if I plug that in, I would have 1 over 0.99 minus 1. That's 1 over negative 0.01. Well, really, that's 1 over negative 1 over 100. When you divide a fraction, you learn that you multiply by the reciprocal. So notice on this that you're getting very small. If I used 0.999, it would get very small. So the idea is when you get real close to the value of the vertical asymptote, you're going to be taking a number divided by some tiny number. And when you take a whole number divided by a tiny number, it gets bigger and bigger and bigger. Okay, look what happens if I do x equals 1.001. Then I'd have 1 over 1.001 minus 1. That's 1 over 0.001. That's 1 over 1,000th. So that actually is 1,000. Okay, so it's helpful to understand why these graphs behave the way they do at a vertical asymptote. That's just because how the arithmetic goes. Again, the bottom line is if you take a number and divide it by something tiny, here's what's going to happen. I can even demonstrate this on the calculator. I'm going to pick a number. It doesn't matter what number I pick. If I take that and if I divide that by something that's tiny, look at this. Look how big the number is. Or here's another one. 6 divided by, now I'll divide by a tiny negative number. Look at that. It just gets smaller. So that's the idea. Okay. Let's do one more on the next page and then we'll finish this, let you do some problems. So again, this one, we have x plus 5 and we're going to factor that denominator as x plus 5x minus 5. That's a difference of 2 squares. So what happens is one of them will cancel out. The one that cancels out gives you a whole. So if you're computing a whole on this, you want to look at 1 over x minus 5, or you want to look at the one that canceled, I'm sorry. So the one that canceled is x plus 5. Set that to 0 so you have a whole at x equals negative 5. Okay, whichever one cancels does not give you a vertical asymptote, it gives you what's called a whole. Now the vertical asymptote will be found by what's left over. So after you cancel that out, you get 1 over x minus 5. So that's what I mean by the reduced form. So now if you set that equal to 0, you're going to get the vertical asymptote. So the one that cancels is what we call a whole. The one that doesn't cancel gives you a vertical asymptote. I'll put this in the graphing calculator and that'll help you make sense of this. So another thing you can do on your whole is if you take the 1 over x minus 5 and you plug in the value of that whole, negative 5, you get 1 over negative 5 minus 5, so you really get negative 1/10. So this whole happens at the point negative 5, negative 1/10. Okay, you just sort of have a hole in the graph. It's not defined. So let me show you how this looks on a graphing calculator. Yeah, this should be something that's pretty helpful to help you understand this problem. So if I put in x plus 5 Notice I'm putting that in parentheses. You have to. And then the denominator, x squared minus 5. Now we're going to put in the original, x squared minus 25, I mean. Again, I'm going to go zoom 6. Now, you see, when you have a vertical asymptote, your graphing calculator is not going to print out that dashed line. But you can tell it's there because part of the graph's going down, part of the graph's going up. Now, there's a hole over here at -5. So the graph is kind of smooth and connected. So you have a hole right here. If I was to go to my table of values, you'll see an error at -5. But what I want you to notice is when you're at -5, on either side of that, see how close these numbers are? The y value at -6 and -4 is pretty close. Okay. Then if you go to +5, you have your vertical asymptote. Notice the 4 and 5 and 6 are numbers that are quite a bit different. Okay, so one of them's an asymptote, one of them's a hole. Okay, all right, so I'm going to let you guys do these problems here. And you need to pause the video, and please do this. Don't just resume and say, okay, here's the answers, I'm going to copy them and get my credit. Don't do that. That's no good. Okay, so if you'll go ahead and check your answers now. Say if you have any problem with this. So number 1, just set the denominator equal to 0. X equals -3/2. Number 2, notice how I factored. And remember, the one that canceled is the whole, so -4 is the whole. The one that's left over is that. And then again, after you cancel it, you end up with 1 over x minus 4. So if you plug the value of the whole in, you get 1 over -8. So if you were graphing this, if you plotted the point -4, -1, 8, that would not be a solid dot. It would be a hole in the graph. Okay, so that's how that goes. Okay, number 3, you'd be real interested to see if you factored this. Okay, so the factoring is 3x plus 1x plus 2. Solve the two equations, you're going to get -1/3 and -2. So that's all about factoring. Okay, and number 4, if you're coming from the left, the graph goes down. Coming from the right of the asymptote, the graph's going up. And number 5 had 2 asymptotes, one at x equals -1, one at x equals 2. So on this one, if you're coming from the left, the graph's going up. If you're coming from the right, the graph's going down. And then it's down on the other two. So that's why we only have the left-hand limit going to positive infinity, but the other things are going down, so that would be -infinity. Okay, all right, so hopefully you did well with that. Okay, next thing we're going to talk about is a horizontal asymptote. And with this, there's kind of a number of ways to teach how to do this, and these things will show up a lot in a Calculus 1 class, so it's really good to get this under control now. Because when you get in calculus, you want to learn calculus. You don't want to have to relearn algebra. So what happens, a horizontal asymptote of a rational function determines how the graph behaves as x goes infinitely to the left or right. Sometimes the graphs will level off, sometimes they won't. So the equation of a horizontal line is always y equals a number, because y is not changing when you have a horizontal line. So on these things here, this one you're going to have a vertical asymptote. On this is going to be at x equals -2. Okay, and the horizontal asymptote is going through y equals 3. Now this time what I'm asking you is something a little different. This says as x approaches -infinity, what this means is if the graph goes infinitely to the left, this graph is not going to swing and go up, it's going to level off at that y value of 3. So a horizontal asymptote, what it means is if you go to the left infinitely, you're getting close to that y value of 3. Next one says x approaches positive infinity. That just means if you're going forever to the right, notice this is never going to touch the asymptote. It's just going to kiss it. So a lot of times I say this, okay? I told my students last semester that I want to make a t-shirt and sell it online that says kiss my asymptote. But I asked how many people would buy it, and they said, oh, the class said, yeah, I'll buy it, and I'd wear it with pride. So maybe that's my ticket to wealth, is to get started and start making a bunch of t-shirts. So anyway, that would be 3. Okay, so that's how that goes. The next problem, the vertical asymptote is x equals 0, which is the x-axis. Horizontal asymptote looks like that is y equals 0. And again, this means as x goes forever to the left, the graph is getting close to a y value of 0. And if the graph is going forever to the right, to positive infinity, the y value is closing in on 0. Okay, so that's what the meaning of a horizontal asymptote is. A good way to look at a horizontal asymptote is to look at something like a world record in the Olympics. Like, for instance, in the 100-meter dash, the world record, I don't know what it is, but it's around 9.8 seconds or something like that. But no human being will ever run this race in 9 seconds. We don't have the body to do that. Unless we start replacing our legs with bionic limbs and stuff. But what happens is world records continually are broken, but they're broken at smaller increments. So what the fastest human being may end up traveling, maybe 9.6 is the best we'll ever do. So you can think of a horizontal asymptote that way. Okay, next thing I want to talk about is the rules for how you find a horizontal asymptote. So you have to know about the degree of the numerator. If the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote that's y equals 0. An example of that would be, see, the degree of the top is 1. The degree is the highest exponent. The degree of the bottom is 3. So since 1 is less than 3, that horizontal asymptote is y equals 0. Now, another way to explain this to students is if x is infinitely big, then the 1 doesn't make any difference. Okay, if x gets bigger and bigger and bigger, infinity minus 1 is still infinity. So you end up with x over x to the third, which really is just 1 over x squared. And if you do 1 divided by a big number, that goes to 0. Anytime you take your calculator, and I'll just show this on the calculator, if you do something like this, if you do 1 divided by a really big number, we get something that's close to 0. That's in scientific notation. So if I just put a bigger and bigger and bigger number in there, it's just getting closer to 0. Okay, that's y. Okay, next case would be if the degree of the numerator equals the degree of denominator, then it's the horizontal asymptote's a ratio of the leading coefficients. So if you look at this example 2, the degrees are both equal to 1. A degree is the highest power. So what you do is, again, if x is going to infinity, who cares about the numbers? You get 3x over 2x. X's cancel out, so trust me, if x gets infinitely big, then you're just going to approach 3 over 2. So what you do is you look at the numbers in front of the highest power. That's called the ratio of the leading coefficients. Okay. The third and last thing that can happen is if the degree of the numerator is bigger, then there is no horizontal asymptote. So in this problem, the degree of the top is 4. the degree of the bottom is 2, so that means there is no horizontal asymptote. Now, what I want to talk about here is that you can get what's called a slant asymptote, and you only get this if the degree of the numerator is greater than the degree of the denominator by 1. So 2, you have a degree of 2 and a degree of 1. 2 is bigger than 1 by 1, so you get a slant asymptote. Now, this is something you'll do in calculus, and this is something that some of you may need to go on Google long division algebra. If you just Google long division algebra, you'll get all kinds of videos on how to divide. And students a lot of times have a very limited background in doing this. So I'm going to show you one example. And when you do the division algorithm, it's a 4-step process. You divide, you multiply, you subtract, and you bring down the next number. So the first thing we do on this is we divide x squared divided by x, which is equal to x, and we record that. And you only look at the highest powers, you don't look at anything else. Now when you multiply, you're going to take the x times x minus 2. That's a distributive property, so that will give you x squared minus 2x. You line that up underneath the factors. Then you subtract. So if I do x squared minus x squared, that's nothing. And then if I do negative 1x minus negative 2x, that's negative 1x plus 2x, so that's plus 1x. So that takes care of the subtraction. Then you bring down the next number, and then you have to start over again. Okay, so we got one more loop. You have to do this until you get a remainder. So now what I do is I look at this and this, and I divide them. So if I do 1x divided by x, that's equal to positive 1, so you record that. And then you multiply. So now you would do 1 times x minus 2. And if you do that, 1 times x minus 2 is x minus 2. Then you subtract. So you do x minus x, which is 0x. And again, you do 7 minus negative 2, which is positive 9. Now, this is what you call your remainder. So what you end up doing when you divided this, you ended up getting x plus 1 and a remainder of 9. Now, you learned how to do this even in elementary school. You take the answer and you put the 9 over the divisor. So what happens is if x goes to infinity, this thing goes to 0. Because if you take 9 divided by an infinitely big number, it goes to 0. So what you would get is the slant asymptote is going to be y equals x plus 1. Don't worry about the remainder. This is what matters, is the result of that division. Okay? So that's how that goes. Okay, going to the next page. On here, we're going to do the vertical asymptotes, okay, or the horizontal asymptotes. So the degree of the numerator on this is 2. Degree of denominator is also 2. So again, what happens is if x goes to infinity, the only thing that matters is the highest powers. That's all that you care about. It's not that those things cancel out, it's just they don't make any difference when x is infinitely big. So you end up getting, that becomes 3 over 1. So you get y equals 3 would end up being your horizontal asymptote. That's how you handle it if the degrees are equal. Okay, this one, the degree of the numerator is 3, the degree of the denominator is 2. So since the degree of the numerator is larger than the degree of the denominator, that means there is no horizontal asymptote. You would get a slant asymptote on this, but I'm not going to compute this one. You know, I want you to be able to kind of do like the case I did on the previous page. Okay, next problem, the degree of the numerator is 1, degree of denominator is 2. So since the degree of the top is less than the degree of the bottom, y equals 0 is your horizontal asymptote. Okay? And then the last one, the degree of the top is 1, degree of bottom is 1. So since they are equal, the horizontal asymptote again on this, just realize that the only thing that matters is the highest powers of x and the number in front. So this would be y equals 2/3. Now, on these two problems I just did, your graphing calculator is a great thing to help you understand things. So I'm taking extra time on this video to show you how your technology can be very, very helpful to you. Okay, so I'm going to graph a couple of these things. And let's look at the one I just put in the calculator. If I clear that and I put in 2x, and see that 2x must be in parentheses, divided by 3x minus 4. I'm going to put that in, and then I'm going to go to y equals 2, and I'm going to put in 2/3. Okay, now let me graph this and show you what this looks like. Okay, that red line is the horizontal asymptote. So what's happening, and this is real helpful if you go second graph and open up the table of values, what I want you to look at is this. As x gets bigger, you're going to see that this y value gets close to 2/3. 0.66 repeating sixes is 2/3. So notice the further out I go, see how close they're getting? That you will never reach 2/3, you will just get infinitely close to it. And if I do this in the reverse, if I go to negative infinity, you're going to see the same thing. Look at that. I'm at negative 83. See how close these things are getting? So that is something you can do that'll help you understand visually what a horizontal asymptote is. Okay? And it's worth doing this one. The previous problem, I'm going to do this. I'm going to put x divided by parentheses x squared minus 4. And I'm going to graph that. And then I'm going to put in 0, because that's your horizontal asymptote. Okay, what you're going to see is, again, if you look at the table of values, you're going to see that as x gets smaller, x gets closer to 0. And if x gets bigger and bigger and bigger and bigger, going to positive infinity, then you're going to see it just getting close to 0. So see, that's a real helpful way to use your technology to help you understand what's going on a little better. Okay, the worst way to learn math is always just learning what the teacher told you and not knowing why. If you know why, you'll remember it forever. Okay, pause the video and do these problems right here. Okay, so if you go ahead and resume here, we'll go ahead and see how you did on this then, okay? And I am going to go over the slant asymptote on the last one too and let you write that down too. So the first one, the degrees are both 1. Therefore, the leading coefficients, so that's 1 over 1. The next one, the degree of the top is 2, degree of the bottom is 3. So since 2 is less than 3, that's how you conclude that y equals 0 as the horizontal asymptote. And the next one, the degrees are equal. So notice you have 1x to the third over 2x to the third. That's all that matters is the highest power. So 1/2 would be the horizontal asymptote. Then the next one, degree of the top's 2, degree of bottom's 1. So if 2 is greater than 1, that means there is none. But since the degree of the numerator is 1 bigger, then that's going to mean that you have a slant asymptote. So look what I'm doing on this. And you want to write this down and just kind of go through this and see if you can do this okay. So again, what I'm doing is I have to have a missing term. So I don't have an x, so I have x squared plus 0x minus 6, and I'm dividing that by x minus 4. So what I do is I start by doing the division. X squared over x equals x, so you do that. Step 2, you do the multiplication. So that is x squared minus 4x. Step 3, you do the subtraction. X squared minus x squared is nothing. Now you're doing 0 minus 4x, which is positive 4x. Then you bring down the next term. Start over again. So now you're going to do 4x divided by x, which is positive 4. And then you do the same thing. Multiply. 4 times x is 4x. 4 times 4 is 16, positive 16. Subtract. Negative 6 minus 16 is negative 22. So that is your slant asymptote right there. Now, let me show you what this means on a graphing calculator so that you understand this. So what I'm going to do is I'm going to erase what I had on the previous example. And I'm going to graph the function. And this will go like this. We'll have, parentheses x squared minus 6 divided by, and then parentheses x minus 4. Then, if I go to y2, I'll put in the slant asymptote, which is x plus 4. Okay, so let's graph this, and let's see what this looks like. I'm going to go zoom 6, and this should help you. So notice what's happening, and you're not seeing all of this graph. One thing I could do is I could, change my window a little bit. You can do zoom out, which will just kind of take you further from this. And what you're going to see is, see how it gets close to that slant asymptote? A slant asymptote is the line y equals x plus 4. So what's going to happen is as x gets bigger, it just gets closer to the value of that line. Okay? So, if you look at your table of values, what you're going to find is as x gets bigger, it gets closer to the value of that line. Now see, the value of this line is changing. But these numbers get closer and closer and closer together the bigger you get. So look at that. Okay? And it works the same way if you go to the negative numbers if you go to the left. Okay, all right, so that is going to be the end of this video. I'll do this video in 2 parts because it's a little bit longer. So hopefully this helps you guys to do a good job. Cheers, have a good day.